Good morning, class. We are looking at exam 3 review covering chapters 3 and 4. Chapter 3, differentiation rules. Chapter 4, application of differentiations. And now in this part, we're going to cover section 3.11 hyperbolic functions, 4.1 maximum and minimum values. So what are hyperbolic functions to begin with? Section 3.11 hyperbolic functions. Hyperbolic functions are called hyperbolic because they are defined in relation to a hyperbola, just as trigonometry functions are defined in relation to a circle. Trigonometric functions come from points on this circle, x squared plus y squared equals 1. P has coordinates x comma y, or cosine t sine t. Sine t represents y, cosine t represents x. The unit hyperbola has the equation x squared minus y squared equals 1. P has coordinates x comma y, or cos t sin t, or hyperbolic cosine, hyperbolic sine. Sin t equals y, cos t equals x, then this satisfies the hyperbola equation cos squared minus sin squared equals y. In other words, trigonometric functions on unit circle, x squared plus y squared equals 1. We know cosine squared plus sine squared equals 1. In the case of the hyperbolas, x squared minus y squared equals 1 represents a hyperbola known as a unit hyperbola. Cos squared minus sin squared equals 1. Now, cos or hyperbolic cosine of x has a specific definition. It is equal to e to the power of x plus e to the power minus x over 2. Sin x or hyperbolic sine of x has a specific definition. By definition, it is equal to e to the power of x minus e to the power minus x divided by 2. This gives rise to some identities, as we've seen identities in the case of trigonometric functions. Now we have it with hyperbolic functions. Similarly, for example, cos squared minus sin squared equals 1. Hyperbolic cotangent squared minus 1 equals hyperbolic cosecant squared x. 1 minus hyperbolic tangent squared x equals hyperbolic secant squared x. Sin 2x is 2 sin x cos x. Just for the sake of argument, everybody remembers sine of 2 alpha is 2 sine alpha cosine alpha. So similar to that, cos 2x is cos squared plus sin squared. Now you may remember that cosine of double angle, cosine of 2 alpha, is cosine squared minus sine squared. So there are some similarities, some differences. Then you can solve for cos squared. You get cos 2x plus 1 over 2. Sin squared equals cos 2x minus 1 over 2. And again, you can go back to trigonometric functions, find them similar. Now, here's some definitions exactly like trigonometric functions. For example, tangent is sine over cosine. So hyperbolic tangent is sin over cos. Hyperbolic cotangent is cos over sin. Hyperbolic cosecant is 1 over sin, and hyperbolic secant is 1 over cos. All trigonometric functions are odd except cosine and therefore secant. So sinh is also an odd function. Sinh of minus x is minus sinh x. Cos minus x is cos x. That is an even function. Sinh of x plus y, as you recall, sine of alpha plus beta, cosine of alpha plus beta. So sinh of x plus y is sinh x cos y plus cos x sinh y. Cos of x plus y is cos x cos y plus sinh x sinh y. So again, there are some similarities. There are some differences, but and they can all be easily proven. Now, when you take the derivative of sine, you get cosine. So the derivative of sin is cos. When you take the derivative of cosine, you get minus sine, but the derivative of cos is positive sin. So there are some differences. The derivative of hyperbolic tangent is hyperbolic secant squared x. The derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. The derivative of hyperbolic secant is minus hyperbolic secant hyperbolic tangent. The derivative of hyperbolic cosecant is negative hyperbolic cosecant hyperbolic cotangent. Okay. As we have inverse trigonometric functions, we also have inverse hyperbolic functions. As they are defined as a function of exponentials, their inverse must be defined as a function of natural logs. And it again can be easily proved. For example, sinh inverse x is ln of x plus the square root of x squared plus. You probably remember most of this stuff from pre-calculus. Now, for example, the derivative of sine inverse of x was 1 over 1 minus x squared. Now the derivative of sinh inverse of x is 1 over x squared, square root of x squared plus, slightly different. And the derivative of cos inverse is 1 over square root of x squared minus 1. And the derivative of hyperbolic tangent inverse is 1 over 1 minus x squared. So some clear differences. Now, let's look at some of the proofs. For example, cos squared minus sinh squared equals 1. We want to prove that, and I'm going to remind you that, for example, we looked at trigonometric identities. To prove them, we would start from one side, normally the one which is more complicated. In this case, clearly, the left-hand side is the more complicated side. And we go with the definition. So we replace the cos with e to the power of x plus e to the power minus x over 2, and sinh with e to the power of x minus e to the power minus x divided by 2. So we're going to replace with what is its definition. So the definition of cos, the definition of sinh. Now we want to raise this to the power of 2, and I'm going to remind you that a plus b squared is a squared plus 2ab plus b squared. Needless to say, if I have a negative here, I have a negative here. So if I want to raise this to the power of 2, or this one, first of all, both of them have the same denominator 4. Now what happens to this one? Let me just actually write the top here, just the top. So it's e to the power of x squared plus 2 e to the power of x, e to the power of minus x, plus e to the power of minus x squared. So what is this? E to the power of 2x. This I'm going to write it just the way it is, and we'll see what happens. And this is plus e to the power of negative 2x. What's the denominator? 4. Minus, when you go to this part, you repeat exactly the same thing, except since this is negative, you get negative here. So this is what you get. E to the power of 2x, 2 e to the power of x e to the power minus x, plus e to the power of minus 2x divided by 4, minus this one is identical to this one, except plus becomes minus. Now, I want to discuss this one. E to the power of 0. So 2 e to the power of 0 is 2. I hope you see that. And therefore, we can replace this one with positive 2, this one with positive 2. This negative makes it negative 2. Now we want to put everything on the same large fraction bar. So we're going to put this one as e to the power of 2x plus 2 plus e to the power of minus 2x. Now minus e to the power of 2x plus 2 minus e to the power of minus 2x. And I'm going to erase my work. So clearly, e to the power of 2x and negative e to the power of 2x cancel each other. These two cancel each other. The numerator is 4, 4 over 4 is 1, and that's the proof. So we started with the left-hand side, cosh squared minus sinh squared, and we ended up with the right-hand side, 1. We want to prove 1 minus hyperbolic tangent squared x is hyperbolic secant squared x. If you recall, when and in the case of the trigonometric functions and Pythagorean identities, we had 3 of them. The first one was sine squared plus cosine squared equals 1. And when we wanted to prove the other 2, we started with that one. So we're going to start with this one in the same manner. In that case, we divided both sides. First, by sine squared, we proved one of them. Then by cosine squared, we proved the other one. And since we want to prove this one, we're going to make this one 1. How do we make this one 1? We're going to divide by cosh squared. So let's divide both sides. So obviously, this is 1. This is sinh over cosh, which is hyperbolic tangent. So 1 minus hyperbolic tangent squared. 1 over cosh is hyperbolic secant, so square it. And that is the proof. So I hope you see, in order to prove hyperbolic identities, you act similarly to trigonometric identities. It's very straightforward. So you start with what has already been proved or definition. All right, so we said the derivative of sinh x is cosh x. Let's prove that. So what is the derivative of sinh x? We are saying it's cosh x. Let's show that. So we start with the definition. We replace the sinh with e to the power of x minus e to the power minus x divided by 2. And to differentiate that, first of all, same fraction bar, same denominator, 2, it's just a multiply. E to the power of x. So in other words, let me just rewrite it here. So this means 1/2 of e to the power of x minus e to the power minus x. So if I want to differentiate, this 1/2 remains e to the power of x itself minus this one is itself times -1 by the chain rule. You need the derivative of the exponent. And this becomes plus. And I hope you see that this is the same as e to the power of x plus e to the power minus and minus plus e to the power minus x divided by 2. What is that equal to? Cosh x. So we just proved that. And I'm going to highly recommend you prove the derivative of cosh is sinh x exactly in the same manner. That would be a good practice, everybody. Okay. The derivative of a sinh of 10x squared. As you may recall, I said if you want to differentiate trigonometric functions, just start with the function and never mind the argument first, right? With the trigonometric functions. We're going to do exactly the same thing here. Sinh, the derivative is cosh. Now, you can't write any trigonometric functions or hyperbolic functions without their arguments, so you must use the same argument first. Then, by the chain rule, you need the derivative of 10x squared. So the derivative of sinh of g of x, is cosh of g of x, g prime of x, so cosh of u, du dx. So times the derivative of this piece, which is 20x, and that sits in front. So that's pretty straightforward. What about the derivative of cosh? Again, cosh, the derivative is sinh. But you can't just write it without the argument. You must use the same argument. Now, by now, you may know the derivative of square root of x is 1 over 2 square root of x, or just do it as follows. This is x to the power of 1/2. Its derivative is 1/2. X to the power of 1/2 minus 1, or negative 1/2. Goes down, becomes positive, and becomes a square root times 1 over 2 square root of x. You put this in the numerator. The final answer is sinh square root of x over 2 square root of x. So pretty straightforward. Hyperbolic tangent. The derivative is hyperbolic secant squared. So we're going to write hyperbolic secant squared. But you can't do it without the argument, so you have to have the same argument. So you put the same argument. By the chain rule, you need to tag along its derivative. The derivative of 1 is 0, so ignore it. E to the power of 2x is itself, e to the power of 2x times the derivative of the exponent. And you put 2e to the power of 2x in front because it looks better that way. Okay, everybody? So that's how you differentiate hyperbolic functions. Now, what about sinh inverse of x squared? First, if you look at the sinh inverse is 1 over square root of x squared plus 1. When the argument is x, but what if it's not? Then whatever that argument is, for example, if it's u, then you have to put the u here. But by the chain rule, times its derivative du dx, which goes to the numerator. If it's g of x, then g of x to the second power, and then times its derivative, which is g prime of x. So take a look. You're going to put 1 over the square root. So something goes here to the second power, and something goes here. What goes in here? Exactly what you have here, x squared. Okay, so what goes in here? The derivative of x squared. This is by the chain rule. You rewrite it. 2x over the square root of x to the power of 4 plus 1, and you're done. Sinh inverse of tan x, you do exactly the same thing. You put this piece, something goes in here to the power of 2, and something goes here. What goes in here? Exactly what you have, the same function. This is g of x. So you put g of x or tan x here. What goes in here? G prime, the derivative of tan x, secant squared. So tan x goes here, secant squared goes here. Now, as you should know, tan squared plus 1 is secant squared. So this is the numerator, and the denominator is square root of secant squared. Now, this is important to know that this is equal to absolute value of x. So this is equal to absolute value of secant x. When you divide this by this, you can drop the secant x, but you have to keep the result in an absolute value, okay? Because it depends whether it's possible. In any event, if it's positive, positive comes out. If it's negative, you get the squared, and then you write the opposite of that, which is positive. So let's erase this. What about y equals e to the power of x cosh x? We recognize this as the product of e to the power of x and cosh x. F times g. And so f prime g plus g prime f prime e to the power of x is itself, times g, which is cosh x, plus g prime cosh is sinh, and times e to the power of x. All you have to do, factor e to the power of x out. You get cosh x plus sinh x. Now, something interesting happens. So if you look at cosh x and sinh x and add them up, let's see what happens, everybody. Let's add these two. And I'm going to put it here. When you add them, you get the following. The numerator is e to the power of x plus e to the power minus x for the cosh, plus e to the power of x minus e to the power minus x for the sinh. And they have the same denominator too. These two cancel each other, and you get 2 e to the power of x over 2, and the answer is e to the power of x. So you can say e to the power of x times e to the power of x, making it e to the power of 2x. So cosh x and sinh x, the sum is e to the power of x, everybody. Okay, so let's switch gears. Chapter 4, application of differentiation, 4.1, maximum and minimum values. So 4.1 maximum and minimum values. Here's the definition. Critical point, short CP, a critical number or point of a function f is a number c such that f prime is 0 or f prime DNE does not exist. So for example, let's find the critical number for y equals x to the power minus 2 times ln x. Here's the process. Number 1, find f prime of x. Well, x to the power minus 2 times ln x, f times g, and we need f prime g plus g prime f. F prime is negative 2x to the power minus 3 times ln x, plus ln x gives you 1 over x times the first piece, x to the power of negative 2. This is x to the power of minus 3. And so between these two, x minus 3 is in common, so we get negative 2 ln x plus 1. And this can go down, becomes x to the power of positive 3, x cubed. So that is y prime or f prime of x. This is step 1. Step 2, f prime equals 0, f prime doesn't exist. When we deal with a fraction of the form a over b, which is the case here, a fraction is 0 when the numerator is 0. A fraction is undefined or does not exist when the b is 0 or the bottom. So let's write y prime equal to 0. That means the numerator is 0. We move the 1 becomes negative 1 divided by negative 2. ln x is positive 1/2. And if you go to the exponential form, x is e to the power of 1/2. And you keep it as such because it's an exact answer, everybody. Y prime does not exist. That means the denominator is 0. That means x equal to 0, but it can't be. Why is that? When we go back to the original function, and let me erase my, please understand. This is ln x over x squared. This function, the domain for ln x, so it's a combination of natural log and a rational function, 1 over x squared. This has a domain. As you recall, the domain is 0 to infinity. In other words, all positive values. So we don't have to even worry about the denominator because the denominator says x can't be 0. And so basically, if it's 0 to infinity, 0 is not included. So it has got to do with understanding the domain of functions. Formal definitions, maximum and minimum points on a curve. Local or relative extreme values. Extrema is the plural of the Latin extreme. A local minimum is the minimum value within some open interval. Local minimum occurs at a point C in an open interval of a to b in the domain if f of c is less than or equal to f of x for all x values in that open interval. On the other hand, a local maximum is the maximum value within some open interval. Local maximum occurs at a point C in an open interval, a to b, in the domain if f of c is greater than or equal to f of x for all x values in the open interval. So if you look at this, the bottom line, peaks and valleys. Local minimum, local maximum. Local minimum, local maximum. Peaks and valleys. Absolute, the difference is it's in the entire domain. So absolute, also known as global extreme values or extrema, are either maximum or minimum points on a curve. Absolute minimum occurs at the point if f of c is less than or equal to f of x4, and that's the key. All x values in the domain. Absolute maximum occurs at the point C if f of c is larger than or equal to f of x4. All x values in the domain. So as we look at these two cases, local mean, local max, local mean. Please understand this is local mean. Also, it's an absolute minimum. Why is this the absolute minimum? Because no other point has a smaller y coordinate. Local max, local mean, local max. This local max is the absolute max as well, because no other point has a larger y coordinate. Local or relative extreme value. Fermat's theorem indicates if a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists at C, then f prime must be 0. So take a look. Local max, local mean, local max. Now, over here, nice and smooth curve. So f prime exists, and if you draw a tangent line, it's horizontal, f prime is 0. But this one is a sharp corner. So f prime doesn't exist. This is the local max because there is no other point having a larger y coordinate. It is also an absolute. Note, local extremes in the interior of the function occur where f prime is 0 or f prime is undefined. Maxima and minima of a function always occur at critical points. But critical points are not always maximum or minimum values. We have to further investigate them. Extreme value or closed interval theorem. If f is continuous over a closed interval of a to b, then f has a maximum and minimum value over that interval. Two things. The function must be continuous and the interval must be closed, meaning the endpoints are included. So in this case, absolute max, absolute mean. Max and mean at interior points. By the way, generally speaking, when we say max and mean, we mean absolute. In some instances, they mention both absolute and relative. In this case, absolute max, absolute mean. Max and mean at endpoints. By the way, endpoints can be only absolute. They can never be local. Absolute max, absolute mean. Maximum at interior, minimum at endpoint. So to find absolute max and mean by extreme value, also called closed interval theorem, number one, find the critical points and evaluate the function at those points, f of all those critical points. Number two, find the values of the function at the endpoints, f of a and f of b. In other words, evaluate the function at the two endpoints and evaluate the function at every critical point in between. The largest value is the absolute max and the smallest value is the absolute mean. Let's look at a couple of simple examples. So here's the process. We want to find the absolute max and minimum value of the function. F of x is 1/3 x cubed minus 9x and the interval of -6 to 0. So here's the process. Extreme value or closed interval theorem. Method. Number one, find CPs. F prime of x equals 0 doesn't exist. Number two, find f of a, f of b, f of c1, and f of c2. That means all the critical points. Number three, absolute maximum is the largest value. Absolute minimum is the smallest value. Before you start, you have to justify usage of the closed interval theorem, which means you have to prove this is a continuous function in the given interval. So what type of a function is this? Polynomial. Recall, all functions are continuous in their entire domain, and that's the key. Any type of a function that you have to be able to come up with the domain. So for example, polynomial functions in general are f of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 plus plus a sub 1 x plus a sub 0, a sub n, the leading coefficient, a sub n x to the power of n is the leading term. So leading coefficient can't be 0. N is a whole number. Whole number we mean 0, 1, 2 to infinity. Domain are real numbers from negative to positive infinity. Now, what is this? Polynomial of degree 3. Domain is all real numbers. That means domain is all real numbers. That means it's continuous from negative to positive infinity. Therefore, it must be continuous in the given interval of -6 to 0. We go back to the process. Step one, find CPs, f prime. Let's find it. So what is f prime? 1/3 times 3 x to the power of 2. So this is x squared minus 9. And we are going to set it equal to 0. That means we're going to factor. This is a squared minus b squared. X plus 3x minus 3. If I set this equal to 0, I get -3 and +3. F prime does not exist, doesn't give us any answer. Phi is a Greek letter representing an empty set. So F prime doesn't exist, doesn't produce anything because F prime itself is a polynomial of degree 2. Now, look at the given interval. Is negative 3 in between? Yes. Is positive 3 in between? No. Can you use that? No. So you can only use the one in between. So in set theory, we say negative 3 is an element of that. I remind you again of this notation reads an element of. Therefore, you're going to go back to the function. So find f of a, f of b, and so forth. Go back to the function, evaluate it at these two endpoints as well as negative 3. So plug in negative 6, 1/3, negative 6 cubed minus 9 times negative 6. Negative 6 squared is 36 times 6 is 216, and because it's cubed becomes negative. 1/3 of that is negative 72 plus 54 gives us negative 80. Plug in negative 3, cube it, negative 27. Negative 27 divided by 3, negative 9, plus 27 is 18. I hope you see if you plug in 0, you get 0. Largest value is 18, so absolute max is 18 at this pair. Smallest is negative 18 at this pair, and we write absolute maximum equals 18 at negative 3, comma 18. Absolute minimum is negative 18 at negative 6, negative 18. This is the way I like to write it. You have to answer the way they ask you for 4 credit. We're going to repeat the question when we find the absolute max and mean for a different function. F of x is x plus 3 to the power of 2/3 minus 5 in the interval of negative 4 to 5. So the very first thing is this justified? Is this function continuous in the given interval? What type of a function is that? We're going to rewrite this as cube root of x plus 3 to the power of 2 minus 5. And ultimately, you're dealing with the cube root. So what's happening is cube root, it gets squared, and then minus 5. So cube root has the domain all real numbers. When you square it, the positive side remains, the negative side flips over, and minus 5, you bring it down. So the domain is all real numbers. So f is a cube root function. It's continuous from negative to positive infinity. Therefore, it's continuous in the given interval of negative 4 to 5. Step 1, find f prime of x. 2/3 times x plus 3 to the power of 2/3 minus 1, which is negative 1/3. The derivative of the inside is 1. We don't have to write it. And we take this down. We rewrite it in this fashion. We want to get f prime equals 0, f prime doesn't exist. Again, I'm going to remind you of a fraction of a over b is 0 when a is 0 and it's undefined when b is 0. In other words, a fraction is 0 when the top is 0. So f prime equals 0 gives us no solutions. Why not? When the numerator is a number, it doesn't matter positive, negative, small or large. It can never be 0. So a fraction where the top is some sort of a number, there is no solution. Now, f prime doesn't exist. You set the denominator equal to 0. What makes this 0 if x is negative 3? Now, the question is negative 3 in between the given interval of negative 4 to 5? Yes. Negative 3 is an element of that. And therefore, we are going to go back to the original function, either in this format or in this format, and evaluate it at a and b, the two endpoints, and there is only one critical point. So let's start with -4. And plug into this function. Now, I hope you see that -4 and 3 is -1. Cube root of -1 is still -1. You raise it to the power of 2, becomes +1. -5 is negative. Clearly, if you plug in -3, this goes to 0, so the answer is -5. If you put 5, you get 8. Cube root of 8 is 2. 2 squared is 4. 4 minus 5 is -1. All of them are negative. The largest one would be this one. The smallest one would be this one. We would write absolute max is -1 at pair 5, comma -1. Absolute minimum is -5 at pair -3, comma -5. We're going to repeat the question. Find the absolute maximum and minimum for this function. F of x is x over x squared plus 2, and the interval is 0 to 4. And the first question is this function continuous? What is the domain? What type of a function is this? And this is a rational function. So a function f is a rational function if f of x is n of x over d of x, where, and of course d of x can't be 0, where n and d are polynomials. The domain of f consists of all real numbers except the zeros of the denominator of f of x, namely d of x. In other words, set the denominator equal to 0 and exclude that. Find the solution, exclude it, that becomes your domain. Now, because this is +2, this expression is always greater than or equal to 2. So this has no solutions. That means nothing is excluded. That means the domain ends up being all real numbers. So f is a rational function and it's continuous on the interval of negative to positive infinity. We explained why. And it's continuous, therefore, over the given interval of 0 to 4. So we are going to go with f prime. To find f prime, we are looking at f over g, and therefore the quotient rule, f prime g minus g prime f over 2, and therefore we are going to say 1 times x squared plus 2. The derivative of the bottom is minus 2x times x over x squared plus 2 quantity squared. Simplification of the numerator, let's see what we get. These two add up to minus x squared. So f prime is minus x squared plus 2 over x squared plus 2. And all we've done, we've come this far. But now we're going to look at equals 0 and does not exist. Equals 0, the numerator is 0. And I hope you see that this means two equals x squared, x is plus minus square root of 2. F prime doesn't exist, means the denominator is 0, and we showed that x squared plus 2 couldn't be 0, therefore when you square it can't be 0 either. No solution. So there are two solutions, square root of 2 and negative square root of 2. Is square root of 2 in between? Yes. Is negative square root of 2 in between? It's negative, no. And by the way, square root of 2 is about 1.41. So We have found all the critical points. We're going to evaluate the original function, this function, at the two endpoints at square root of 2 as well. So first and foremost, the function is this. If I plug in 0, please understand the numerator is 0, the denominator is 2, and obviously I get 0. That's not a big deal. If I plug in square root of 2, square root of 2 squared is 2 and 2 is 4, so square root of 2 over 4. If I plug in 4, the bottom becomes 16 and 2, 18. 4 over 18 or 2 over 9. This is the smallest value. I hope you recognize this one as the largest value. If you don't, you can go to decimal representation. Okay. Think about this, 2 over 9. So if you multiply 4 by 2, a little bit more than 2, you get 9. So if you multiply this one, 2 times 1.41 is 2.8. So clearly it is large. But in any event, absolute max equals square root of 2 over 4, roughly 0.35 at this pair, square root of 2 and square root of 2 over 4. Absolute minimum is 0 at 0, 0. Please understand, when we look at max and mean, absolute or otherwise, we mean the y coordinate. That's why I like to explain the details in this manner. Find the absolute max and minimum value of the function f, where f of x is x squared minus 1 quantity cube in the interval of -1 to 2. So first and foremost, what is the domain of the function? Well, what type of function do we have? This has exponent 2, this has exponent 3. I hope you see just we get polynomial of degree 2 times 3, that means 6. So f is a polynomial of degree 6, therefore it's continuous from negative to positive infinity, and it's continuous in the given interval of -1 to 2. So step 1 is the f prime of x. And to find f prime of x, we have 3 times, we are going to use the extended power of 3x squared minus 1 squared, the derivative of the inside 2x. We put these two together and we put 6x in front. So that's f prime. Now setting it equal to 0, gives us, this gives us 0. This gives us x squared equals 1, or x is plus minus 1. There are three answers. F prime doesn't exist, does not produce any solutions. Why not? It's a polynomial. F prime is a polynomial. What is the degree? 2 times 2. The degree is 4. This one has degree 1. So the degree of this polynomial is 5. But nevertheless, it's a polynomial. So there are two answers. -1 is one of the endpoints. That works. +1 is in between, yes. 0 is in between, yes. Let's evaluate the function at everything. So all of those belong to the given interval. One of them is one of the endpoints. You don't have to repeat it, of course. But you have to evaluate the function at all those 4 points, starting with -1. If I put the -1 class and square that, I get 1. 1 minus 1, 0, 0 cubed is 0. If I put 0 here, this goes away. So -1 cubed or -1. If I put 1, 1 squared is 1 minus 1 is 0, so I get 0. If I put 2, 2 squared is 4, -1 is 3, cube it, 27. Largest value, smallest value. So we write absolute maximum is equal to 27 at 2, 27. Absolute minimum is -1 at this pair, 0, negative 1.